Hi, this is Professor Fernandez. We are working here on video 3 in lesson 6. We're still working on rationalization here as a technique for evaluating limits. And in this example from Calculus Simplified, I'm going to show you a more advanced way, example where rationalization is needed. So I'll zoom in a little bit here. Here's the limit. Limit as x goes to 0 of this function. So I'm going to do the same thing I always suggest you do first, which is try substituting in the point. Maybe this function is continuous at x equals 0, in which case the limit is just the value of the function at 0. So let's try that. So if I substitute in x equals 0 into the numerator, the denominator, already I see a problem, right? I should stop right there. No matter what the numerator is, I cannot divide by 0. So this is not going to work. I can't substitute in x equals 0. I have to do something else. In the previous video, in video 6.2, I reviewed very quickly some of your options. You could graph this function, you could make a table of values, but those two methods are methods that will only give you an estimate, a guess, if you will, at what the limit is. So that's one of the reasons that we're talking here about algebraic techniques for actually calculating the limit. We just saw that we can't evaluate the limit at x equals 0 because the denominator is 0, so we're going to have to do something else. And in the previous video, I talked a little bit of a review of rationalization. So we're going to rationalize this function. How do I do that? Well, I take the thing that has the radical, which is the numerator, and I write it over, right? Except with the opposite sign. So here I'm subtracting, so I'm going to add. And I don't want to change the expression, so I'm basically multiplying by 1 in a very specific way. Okay, so then let's go through the multiplication here. So when this term multiplies that term, I get just x plus 1. And then this times 1, so this times 1 gives me a plus square root of x plus 1. So first outer inner, so negative 1 times square root of x plus 1 is minus square root of x plus 1. And then negative 1 times 1 is minus 1. And then the denominator is just x times this whole expression. Okay, so that's my denominator. And then I simplify. So notice that the middle terms cancel out. So that's the beauty of multiplying by the conjugate. So you only get the first term, the last term, and then notice that there are no more radicals. So that's exactly what we wanted, to get rid of the radical in the numerator. And you might have thought at the beginning of this problem, why would we want to do that? In a sense, because it's the only possible thing in this function that we could try that might work, right? So a lot of calculating limits sometimes is trial and error. So if we continue here, the 1's cancel in the numerator, so those go away. Great. And I'm left with x over x. And I switched the sign. That should go down there to a plus. So x over x times square root of x plus 1 plus 1. And then now same deal. So I have an x here, I have an x here. I can cancel those. So I will be left with 1 over the square root of x plus 1 plus 1. If you've been watching the videos in this series, you probably know what I'm going to say next. I'm going to say that this is an equality so long as x is not equal to 0. Why? Because the original function was not defined at x equals 0. That would have been a 0 in the denominator. This function is, as you can see, if I substitute in 0 there, I get 1 over square root of 1 plus 1, 1 over 2. So anyway, this makes it mathematically correct. But as I've said before, we don't really need all that specificity to calculate the limit because the limit does not care what happens at x equals 0, which is precisely, if I go back up here, where we're asked to calculate the limit. So what can we say at the end of the day? The limit as x goes to 0 of the original function, there it is, divided by x, will be the same as the limit as x goes to 0 of this simplified function, the one we got after multiplying by the conjugate. And then now I can go back to the same first step at the beginning of the video, right? If I substitute in x equals 0, what happens? I get square root of 1 plus 1, I get 1/2. That is certainly a nice number that is not a division by 0 in the denominator, which is what initially happened up here. So that's the value of my limit, and that's an example that illustrates rationalization for use in calculating limits.